are very pleased to have to welcome his family, Cauchy, son Sean, his collaborator, Aziz, his physics advisor, Elias Stein, and another distinguished speaker, Charlie Sherman. So, and basically, before we start the first talk, I'd like to give a small memorial to Elias Stein.
Thank you.
And I'd like to introduce Tony Phillips to say a few words. But then Sullivan will say a few words, and then we'll start. Please do so.
Actually, I thought Dennis was going first, but
can I go first? I want to follow Tony.
Let's see. So I've not been in any of Daryl's classes, but I've heard he took a lot of trouble with them and has his book. And coming up in the elevator, with a student, I said, "Did you ever have a class with Daryl?" And he said, "Yeah." He had a kind of positive look on his face. So I said, "How was it? Was it good?" "Oh, yeah, it was good." And he said, "We used his notes, this book, unpublished book, actually, and that was very good." So just random test of this hypothesis. And the next thing I wanted to mention was in department meetings where Daryl and I were both there, I noticed that he was very concerned about building up analysis at Stony Brook. And he wasn't just a straightforward aficionado of analysis. When he would promote a candidate, there was one candidate who looked like really good in the beginning, but he came and gave a talk, and there were a couple things wrong with the talk. And, he kind of backed off in a reasonable way, didn't keep pushing, kept everything very collegial and had a nice consensus about it. It was nice working. It was kind of a controversial issue, hiring people in different fields, and that's the way he handled it. He was conscientious. And finally, I wrote to Eli and asked about Daryl's work, and I remembered a couple of sentences from his reply that he was very original mathematician, and he did remarkable work. And in particular in the subject of analysis on the Heisenberg group, he was a kind of leading expert in the world. That's all.
I just wanted to say a couple of words about Daryl's teaching. As Dennis alluded to, he was a very popular and effective teacher, and he wrote this book, which is not totally unpublished because here it is. And I thought I would read a couple of just essentially one page from the introduction that gives you an idea. The book is quite idiosyncratic and very much like Daryl. And it means personal of its. It means one kind, right? So this is in the introduction for the students, and he talks about the split brain theory, and he says, according to this theory, the right side of your brain is intuitive. It likes to think in pictures, and it also enjoys language with strong visual imagery. When you think geometrically, you are to a large extent calling on the right side of your brain, since pictures are processed there. The left side is systematic, logical. It is happy with everyday language. When you think algebraically, you are to a large extent calling on the left side of your brain. To do well in this course, you are going to have to learn to use both sides of your brain in harmony. Nothing we do will be terribly difficult for the right side or the left side of your brain. The hard part will be to coordinate both sides. And then he goes on a little bit. I have devised a teaching method based on this philosophy. In many pages of this book, you will see a line down the middle of the page. The material on the left side of the page is intended to stimulate the left side of your brain. The material on the right side of the page is for the right side of your brain. You have not fully understood a proof until you understand it completely on the right side of the brain, completely on the left side of the brain, and until you see that both sides are completely equivalent. You have to be able to go across the page as well as down. At first this will be difficult, But if you are diligent, it will become second nature. Thanks.
Let me introduce our first speaker, Professor Elias Stein from Princeton University. And his title is over there.
So I'm very happy to speak at this colloquium in honor of the memory of Daryl Geller. And all of you knew, of course, what a warm and generous person Daryl was. And I got to know that when I got to know him first, which was when he was a graduate student in Princeton, and at that time, he decided he wanted to work with me. So that's, and let me just say that at that time, what was coming to the fore, at least in one part of analysis, was the interest in the Heisenberg group, because the Heisenberg group arises as a realization of the boundary of the complex ball in Cn via a standard Cayley mapping. And this is a very rich structure. It's a group structure. And so as such, it's also a very good model for the study of domains in Cn which are strongly pseudo-convex. So that's sort of the point of view that was developed there. So it was very important to study the Heisenberg group, and it has a very interesting harmonic analysis. What makes it interesting is that it's a non-commutative group. And the harmonic analysis is connected with a natural Cauchy integral and a natural class of subelliptic operators and cone Laplacians, etc. And so Daryl undertook the study of this harmonic analysis and really developed it very deeply over many years. And as was said, he was certainly the world's great expert in the subject. But besides that, he was interested in many other things, and maybe this was a starting point. And he went on to do many other very interesting things in mathematics. Now, what I want to talk about is that it has a little bit of a link with the Heisenberg group, etc. Only the link is several complex variables, but as I said, the Heisenberg group is a very good model when the domains have a smooth boundary. And I want to talk about what happens. So that's been around for quite a while. I want to talk about a much more recent thing. What happens if the domains do not have a smooth boundary and have sort of minimally smooth boundary given the kinds of problems we want to work on? So just before I start, I want to say that, of course, this is joint work with Loredana Lanzani, done in the last few years. Maybe one or two of you have heard me talk about the subject. I want to say an apology to them. Yes, I'm going to be repeating a lot of things I've said recently, but there are also some new things which are only about a month old. Now, let's start. So I want to start, first of all, by saying that the subject of dealing with minimally smooth boundaries and dealing with them successfully, and these involve many new ideas, was started for one complex variable, so we'll start with that. So I divide my talk in three parts. One is a quick review of work done in the late 70s and early 80s in one dimension. Then I want to come to the more recent work in higher dimensions, and I want to talk about two objects. One is the Cauchy-Leray integral, and the second one is the Cauchy-Szego projection. Okay, so very quickly, the Cauchy integral in one variable, there it is. It's the standard thing. Now, if the domain, now the boundary curve, is smooth, and for smooth here it means a little bit better than C1. C1 is essentially the natural boundary, C1 plus epsilon. Well, if it's C1 plus epsilon, the standard, very classical techniques that are used to study it in case of the circle apply or can be applied, and one has standard results. For example, the famous theorem of Marcel-Ries that the Cauchy integral is a bounded operator on LP. Now, the more recent work of the 70s and 80s is what happens when epsilon is 0, for example. Now, all the standard techniques break down, and so you need new ideas, and these were developed by a number of people. First, in the case when the curve is a little bit less than C1, Lipschitz. So it has, instead of continuous first derivatives, it has bounded first derivatives. And then somewhat more generally, in that period by Calderon, Kaufman, McIntosh, Mayer, Guy David. And then out of that came a development, a very important development in singular integrals called the T of 1 and T of B theorem, which I will very briefly discuss because we're going to be using this, its higher dimensional analog. So I stated very quickly, you have an operator with a kernel whose singularity is along the diagonal, and it satisfies a standard kind of inequality of size, differential inequality near the diagonal. And then it's got to satisfy certain cancellation conditions because the operator doesn't converge absolutely. And with those conditions for the operator and its formal adjoint, the theory says that this is a bounded operator on L2 and then on LP for all p's between 1 and infinity. So that is the theorem. I'm just going to cite that theorem, and that comes out of this one-dimensional theory, but it's an n-dimensional theorem. And let me just very quickly show you how this arises when you look at the one-dimensional Cauchy integral. You can actually think of two alternate operators with kernels k and k prime. In one of them, you see, it's given by a Cauchy kernel with a function x comma a of x. That's the curve, the Lipschitz curve. A is a Lipschitz function. And so the kernel is given either as k of x, y, and this 1 plus I, a prime of y, that's basically the measure dz. And so that's one variant. Now, in this variant, for the cancellation conditions are very good because this kernel maps 1 to 0, for example. But the differential inequalities fail because we can't differentiate anymore. And in the second one, we do have the differential inequalities because A can be differentiated essentially once, but we don't have the cancellation conditions. So the Cauchy integral is sort of a complicated, more complicated version of this, but basically this is at the heart of that. All right, so now I want to mention that there is another natural operator that arises, and that's called the Cauchy-Szego projection. And that's, you take the domain, you take L2 on the boundary of the domain, and you take the subspace, the closed subspace of L2, which arises as boundary values of holomorphic functions, and you take the orthogonal projection operator on that. And now, in the case of the unit ball, this projection operator is the same as the Cauchy integral. And one might ask the same kind of questions. Is it bounded? Now, this has to be dealt, or was dealt with, in the case of one complex variable, by completely different methods. And the idea was, you know the theory for the unit disk, then you can obtain the theory, at least for a simply connected domain, by introducing the conformal mapping. And then if you look at S, and S0 being the Cauchy-Szego projection for the unit disk, you can go back and forth with a simple transformation, which involves the square root of the derivative of the conformal mapping. And then the whole thing is reduced to a problem of the standard Szego kernel. It's an LP problem, but it's an LP problem now with a weight, and the weight is the weight, that derivative, the absolute value of the derivative of the mapping raised to a certain power. And you have to know that this belongs in one of the acceptable so-called Muckenhaupt weight classes. And all of that was done, and I mentioned the references. So that's the thing. Now, finally, I want to say that there is another approach which actually links both the Cauchy integral and the Szego kernel, and works in the special case when the boundary is actually of class C1. And that is, there's a universal identity which links the Szego projection and the Cauchy kernel, and it's given right there. It's a nice little identity that Kurtzman and I discovered a while ago, and it actually is valid in any number of dimensions. It's just a question about two projections, one which is an orthogonal projection and the other one which is possibly a non-orthogonal projection. And so one can, if one knows that C minus C star, C being the Cauchy operator, is compact, then one can invert I minus the identity after using a little play with the Fredholm theory, and one can obtain the result in that case. All right, so much for a quick tour of one complex variable. Now we come to the the question is, so for a long time it had puzzled me what can be the corresponding results in higher dimensions. Now, there are lots of reasons why this should be puzzling. Let me just say this. Here are some of the issues that arise when you want to generalize the Cauchy integral in higher dimensions. So the first issue is that as opposed to the Cauchy integral in one variable, there is no unique God-given notion of a Cauchy integral for a domain in Cn. Okay, we'll come to grips with that. We'll see that there are certain classes of integrals that play the role, but they have much flexibility, and it's a question of choosing one of these. The second thing that you don't see in one complex variable is the notion of pseudo-convexity. So if you've studied several complex variables, you know that the boundary of the domain being pseudo-convex is going to be a fundamental issue, one way or the other. And pseudo-convexity, if you have a boundary function, involves essentially two derivatives and not one derivative. So even to get started to think about the problem, you realize sort of the boundary of regularity should be somewhere with two derivatives and not one derivative. All right. And that's what I say here, that the results are expected to be those that are near C2 as opposed to C1. So now the first question, so what do we want when we say a Cauchy kernel? We want a Cauchy integral. We want an integral that takes a function on the boundary of a domain to a function in the interior, which has the property that somehow it has certain naturality, because there's, of course, so many choices of operators. But we want it to be a projection operator. That is, starting with a function f of w on the boundary, which arises as the boundary value of a holomorphic function, when you plug that in there, c of f of z should reproduce that function. And secondly, no matter what that function f is to begin with, as long as the integral makes sense, we want c of z, f of z to be holomorphic. So whenever we have that, we'll speak of a Cauchy integral. Now, it turns out that a family of satisfying at least A and B of those properties were developed already a long time ago by Fantappie and Koppelman, and various people. And there's a very nice sort of magical formalism that takes place. One has to find a form in Cn whose coefficients are G1, G2 up to Gn, a global form. Capital G is also a way of writing it. And then one takes this delta, which is going to be the denominator, and one wants to make sure that this is going to be a function of z and w, and w is going to go on the boundary, and z is going to be on the interior of the domain. One wants to choose this g such that this inner product is non-vanishing when z is in the interior. And then one takes this form g and one wedges it with d bar g wedged n minus 1 times, and then one gets a form of top degree, and so you can integrate this on the boundary. And by the way, you observe that whatever choice you make in one complex variable, you will get the Cauchy integral. There's only one answer that you will get. Now, the question is, how do we find those g's?
Universal? Do they depend on omega?
Yes, you're going to have to find the form depending on omega. But whatever form, at this stage, whatever form G that you get that satisfies that, you will obtain the fact that G reproduces holomorphic functions. That's a clever use of Stokes' theorem with things drop out very nicely. Okay, there's certain magic in all of this. All right, I'm not going to go through this magic. Now, Leray studied this and in the 1950s, and he was able to construct, now the idea is to construct a G which is holomorphic in Z. You see, and he was able to construct such a G, we're going to see, just by taking for rho to be a defining function, and we take, so that's a function of W, a defining function for the domain. We take D of, so that's still a function of omega, and then when you look at this denominator, it's G in a product Z minus W. It's just a linear function in Z now. It's obviously holomorphic. And he observed that when the domain is strictly convex, then this is non-vanishing. And so this gives you a nice reproducing formula and has all the properties you want. Now, later on, when the natural class to consider more natural is not convex, but strictly pseudo-convex, and then this doesn't work, and you have to do a variety of things. And Henkin and Ramirez did this all under the assumptions that the domain has a smooth boundary. So at least you can define this Cauchy integral. Now let's go on. So there are several notions of convexity that enter, and I'm just going to say very quickly, for a domain with a defining function rho, there's the notion of strict convexity, which means that for this defining function, the corresponding tangential Hessian is strictly positive definite on the boundary. And then there is an intermediate, weaker notion where you require the convex, the strict convexity only in the directions of not the whole tangent plane, but what's called the complex part of the tangent plane, which is a co-dimension 1 subspace. It's the complex, it's the part which is invariant under multiplication by I. And then there's strong pseudo-convexity, which looks like this, except you take these complex derivatives. So, and there is an implication that goes from the top to the middle down. So there are these three notions. And this strong C-linear convexity has a very nice geometric interpretation in the case of a smooth domain. Is if you take any boundary point W and you take the tangent plane, and now you take the subspace T sub C of W, which that's the complex part of the tangent plane. And then you take any point in the interior, then the distance of that point to the tangent plane, that's the Euclidean distance, should be greater than a constant times Z, the distance of Z minus W squared. And of course, if you take the full tangent plane and write this corresponding inequality, that is essentially a strong convexity. All right. So those are the notions that are in the background. And now we would like to talk about the domains of minimal smoothness, and that will involve, to begin with, domains that are of class C11. So they will have essentially two derivatives. It'll mean a function will be of class C11 if it has a first derivative, and the first derivative is a Lipschitz function. So that's the definition. Now, in that general context that we're going to be working in, we can define a domain to be strongly C-linearly convex if it satisfies this inequality with respect to the distance, which was satisfied in the geometric case when the domain was smooth. So here is the first theorem, which partially solves this problem, at least in the case of the domains which are strongly C-linearly convex. If they're of class C11, which means that the defining function that we use has this minimal degree of smoothness, then the Cauchy-Leray integral, which I had before up here, then this operator is a bounded operator on L2, and then once it's a bounded operator in L2, one can also prove that it's a bounded operator on LP. So that's the first theorem. Now let me just say a few things which will put it in context. First of all, it can be shown that in various settings, this result is sharp. Of course, when you say a result is sharp, it's always a question of putting the result in a certain setting. But the C2-ness, which is C11, cannot be replaced by merely assuming the domain is of class C2 minus epsilon. There are examples worked out by Barrett and Lanzani for very special domains. They're Reinhardt domains, they're circular domains, they have a circle action. And therefore, you can use Fourier analysis along the circle, the standard Fourier analysis, and make a very good, strong analysis of L2. And you can see that it would fail by some examples that you can write of these domains, where you replace C2 by C2 minus epsilon. Even if you have this strong C-linear convexity defined geometrically, as I said. And in the C infinity case, it can fail when you drop strong pseudo-convexity. So both of these things are inherent in the problem. The problem is, of course, in some special examples, you can get results when these conditions don't hold. But in that case, the measure on the boundary, which we are using in defining the L2 and LP spaces, which is the induced Lebesgue measure on the boundary, has to be replaced by a measure that has singularities that reflect the failure of these things. So in special examples, this can be worked out. But it doesn't change the nature of this. Now, here is another very special feature of CN, which was an eye-opener, even though it was there all the time to be seen in plain sight. And this has to do with what you can observe just on the Heisenberg group, and which makes it different from what happens in one complex variable, and makes things quite different and much simpler in a certain sense. And that is that the basic Cauchy kernel that arises is itself a first derivative of another kernel which has the right homogeneity, so that you can do some integration by parts without losing anything. You see, that's the exact formula on the Heisenberg group. It's a convolution with that kernel. Now, if you were to do this in one variable, you'd get the log. The 1 over z is the derivative of the log, and the log doesn't have the right thing. And the nice things that you can obtain from that don't work. All right. So, and ultimately, we're going to reduce the proof of this theorem to a T of 1 theorem, which I mentioned briefly above, but a very simple version of a T of 1 theorem. All right. Now, let's go on. So, here is a basic technical question which arises. It's sort of an interesting question. If you go back and look at the formula which defines everything, which is that formula, and you look at G, and G is given in terms of d rho, G equals d rho up there, you will see that this formula involves second derivatives of the defining function. And we're trying to prove something which is of class C11, which means that the first derivative is merely Lipschitz, which means that the second derivatives, yes, they exist, they're L-infinity functions, but they're only defined almost everywhere, and hence are not necessarily defined on the boundary because that's a lower dimensional set. So one somehow has to get around that because essentially the second derivatives of a C11 function cannot be in any way defined. But what happens is because of the very nature of these kernels, of this formula, the second derivatives that arise are all tangential in some sense to the boundary, in a geometric sense. And if the second derivatives are tangential, then they are definable almost everywhere with respect to the boundary measure. So that's the important technical point, that you can define them and you can do the approximations with them, because we're going to have to replace these things by smooth things, and pass to the limit we need smooth things because we do need to do an extra integration by parts for various things to work out. So I'm not going to be able to do this, but let me just, here's the question, and here's a question of asking, we start with a function f, which is of class C11, and we want to be able to define d bar df, that's basic kind of thing, and integrate it on the boundary, wedging it with some appropriate thing. So that requires that we have a notion of what that thing is. And the answer is that you can do that in a natural way, and you can actually approximate, if you can find a good approximation for such an f globally by C infinity functions, such that the appropriate second derivatives, which are the J stars, which are the induced forms on the boundary, will converge boundedly and almost everywhere to a limit. And that limit will play the role of all the things you need. So you can get around that. And now there are a few other nice things to observe. That is that there is a natural measure. I don't know how much time I have. That there's a natural measure on the boundary, which is given by the defining function. Again, this is in the class C11 when you are in the strongly C-linearly case. It'll also work in the C2 case when things are strongly pseudo-convex. You do this integration against this mixed form. Notice again that we're involving second derivatives. But these things exist almost everywhere. And it turns out that this integration is essentially, with respect to a measure, d mu, we call this the Lévy-Leray measure, and it's equivalent to the induced measure up to a density which is bounded above and below. And it can be given by this formula up here, where the determinant of this derivatives in the boundary directions, this is the Hessian of the, makes sense almost everywhere on the boundary, and everything is okay on the boundary. So we can therefore realize the Cauchy-Leray integral as an integral with this measure. That's the measure we're going to work with, which is equivalent to the induced Lebesgue measure, divided by this denominator. And so now there is a geometry, sort of a controlled geometry that we have to work with. There's a distance which is given by this denominator. And this distance gives you a family of balls which are not equivalent to Euclidean balls, but have a diameter r in the complex tangential direction and a diameter of essentially r squared if you look at this distance in the normal direction. And that's the natural, and they involve a certain distance. Well, this we know very well from the Heisenberg group and the various generalizations, that there should be such a controlled distance. And with respect to this controlled distance, once we have a distance and we have kernels that satisfy this, then there's a general theory of spaces of homogeneous type, which says that when we have an operator whose kernel is controlled by these things, then boundedness on L2 will lead to boundedness on LP. And there is also a theorem which says if such operators satisfy the kinds of hypotheses of the T of 1 theorem, we can prove that they're bounded on L2. So that would do the theory if we can do the cancellation properties. So that's the important point here. So let me just very quickly get to this. So here is how we get the cancellation properties and this integration by parts, which says that we're going to use the fact effectively, approximately now in this setting, that the Cauchy integral, the kernel, arises as a derivative. So we look at this auxiliary operator, which is defined on one forms, S of H, where H is this wedge, which is not the full wedge. The full wedge would have a D, be an extra D bar rho. And we observe that by integration by parts, the original Cauchy integral is given by this operator acting on df plus a rather harmless error term on f. In fact, it's a negligible operator. It maps, let's say, L infinity to functions which are relatively smooth. And the same sort of thing happens for C of L. So now if we want to check the cancellation conditions, and I didn't say what those cancellation conditions, but basically what they say is take a smooth bump function which lives on a ball of radius r, where the ball size here is determined by this distance, and whose first derivatives grow in a way corresponding to the size of the ball, basically 1 over r in the good direction, and in the bad direction, the derivative goes like 1 over r squared. If you are to apply your operator, what you have to check is that the L2 norm on such a bump function is what you expect it to be. So in some sense, the cancellation condition is a check that you get the right inequalities, but when restricted to smooth functions. And that sort of takes care of the cancellation that is taking place because it's testing it on smooth functions. So now we can do the test once we have that, because instead of f, we have this bump function. And then we can put d of f, because that involves the first derivatives. And we can now test it against 1 over something which is of the size 1 over the power delta to the power n minus 1. And that is integrable. This is on the good side of integrability. And just a very simple test to show us that we get. And here is very quickly an argument which shows you how the integration by parts works. I'm not going to go through it, but basically it is that the derivative of 1 over delta to the power n minus 1 is basically 1 over delta to the n, except for constants, and lower order terms, which have an error of the form z minus w, and that makes everything good. And therefore, that's basically the integration by parts. And once you have that integration by parts, but in order to make that integration by parts work, you actually need to approximate all these functions which define the kernels by things which are smooth. And therefore, you also need that lemma about the restriction. So that is how one goes about. This is a very, the details are extremely painful to write down. I've spared you this. But that's the first theorem we proved, which is that for domains which are what are called strongly linearly convex and are just minimally smooth, they're of class C11, the natural integral, Cauchy integral, you might say natural, I think quite natural, which was studied by Leray, does do the job. Now the question is, what happens when we are dealing, you see the more natural condition on a domain is strong pseudo-convexity. And now there is another theorem which deals not with this operator, but which deals, as I mentioned, in one complex variable. There was another operator which was quite natural, which is the Cauchy-Szego projection. And now this will actually help us do the corresponding theorem for the Cauchy-Szego projection. So let's come to that second theorem, also a very recent result where we have now checked everything and it is okay. Also a little hairy. Again, now we start with a domain, and now it's strongly pseudo-convex and of class C2. All right? Then the statement is that the Cauchy-Szego projection. So what is the Cauchy-Szego projection? It is, you look at this domain, and you take the induced measure on the boundary. It's, of course, well-defined. The domain is of class C2. You don't even need that. You have an induced measure. And then you have an L2 space, of course. And then you have a closed subspace of that L2 space. That's a subspace of those functions which arise as boundary values of holomorphic functions in the interior. That's a little technical how to exactly characterize this, but all the characterizations turn out to be the same. So there's a natural subspace, and you take the orthogonal projection, and that is the Cauchy-Szego projection. All right? So that is the theorem that the Cauchy-Szego projection is a bounded operator on LP when the domain is of class C2. And I remind you that in one complex variable, the corresponding theorem was the domain basically was of class C1. There are slight variants of this, but basically just Lipschitz by itself was not enough, but C1 was enough to prove this inequality. So now let me make a few remarks. First of all, if you go back to the simplest, the model domain, which is the unit ball and then its boundary, then we had the Cauchy-Fantappie. That's certainly a domain which is strongly C-linearly convex and hence certainly strongly pseudo-convex. We had the Cauchy integral, and that turns out to be the same as the Cauchy-Szego projection. And it's given by this very explicit integral with this denominator and integration on the boundary. So that's one remark. Now, if the domain is sufficiently smooth, then going back to work of Charlie Pfefferman, which he did when he studied the Bergman kernel in his theory of mapping, holomorphic mappings of domains, he found very good asymptotic formula for the Bergman kernel and just as well for the Szego kernel because there is a close connection in the appearance and the way you go about finding these formula. So if the domain is sufficiently smooth, then the corresponding Szego kernel gives you a singular integral which is sort of recognizable and can be worked out by the old techniques. However, when you get down to class C2, I think these methods don't work because you need to osculate by high degrees and you can't get started. So you need to look at it from a different point of view. So let me just spend 3 minutes explaining how this will follow from ideas that I have mentioned, and I think I have, I must be running out of time, so I'll just state the main idea. The main idea is to try to go back to the identity, which is to try to get one Cauchy integral. Now we're going to get a Cauchy integral, but it's not going to be unique. In fact, we're going to get a whole family of Cauchy integrals, and these will be adapted to our problem. All right? So we're going to get a Cauchy integral, which is called C epsilon, depending on epsilon, which will be a bounded mapping from LP to LP, and the Cauchy integral will be given by a Cauchy-Fantappie integral for an appropriate kernel, but the kernel isn't quite right because it's not quite holomorphic. And therefore, that kernel has to be corrected, but that's the R, by a solution of a D-bar problem. Okay, it gets a little bit hairy, but so anyway, that's going to be the C epsilons. Now, what about those C epsilons? Each of those will be bounded mappings from LP to LP. So they will have, in some sense, solved the problem for strongly pseudo-convex domains, but there are so many of them, so they're not natural. But now it happens that it's very good that there are many of these, because they're going to be very helpful in this problem. In fact, for every epsilon, there is one of these. And the important thing is, again, if you look at C epsilon star, the adjoint minus C epsilon, in this Kurtzman identity, which I showed you earlier, you wanted to have that difference is completely continuous. Unfortunately, and this was a big barrier, we didn't see how to prove that it's completely continuous. But we can get around this by proving that this difference can be divided into two parts. One which has a small norm as an operator from LP to LP, and the other one, while it may have a huge norm, is still a bounded mapping from L1 to L infinity. Assuming for a moment that we can do that, and I will tell you maybe in 2 minutes what are the steps involved in that, then our identity becomes S minus identity equals this. That's the first, that's the identity that we had, and now we break this up into two parts. Now let's see that the right-hand side is a bounded operator from LP to LP. It is because we claimed it for this Cauchy integral, that's this one. The B epsilon is a bounded mapping from L1 to L infinity. So if P is less than 2, it's a bounded mapping from LP to L2. And S is, of course, a mapping from L2 to itself. And so being in L2 is being in LP. So this shows that the right hand is a bounded mapping from LP to LP if P is less than 2. And now, if the norm of A epsilon is small, we can just use a Neumann series to invert. And if P is on the other side of 2, we just use the adjoint of this, and it goes in the other way around. So that's what we have to do now. Actually, to construct this, there are 4 steps. And let me just maybe flash them on the board. We, first of all, start with this denominator, which was the denominator in the Leray integral. And following the idea of Henkin and Henkin and those guys, we have to add a second order term to get this inequality. The Ramirez-Henkin inequality yields this term for Z near W, but it involves the second derivatives of the defining function. And hence, if we use that in our denominator, we're screwed because we have no smoothness left. And we need to have some smoothness for our kernel in order to make any of these theorems work. So what we do next is we replace the second derivatives by an approximation by a C1 function or a C infinity function, which is very close, and that's basically the epsilon that we want, to the second derivatives, and then we form a new kernel with it, and then we have to take care of what happens when Z is not near W, and we have to add a very trivial change. And then with that, we can write down a Cauchy-Fantappie kernel, but it's no longer holomorphic in Z, and so we have to correct it by a D-bar problem in the region. And then that's the third point. And now finally the last point is we have to find a distance which is sufficiently small. These second derivatives are continuous by assumption, so the differences at 2 points will be less than epsilon if the difference is sufficiently small. And now we restrict our operator, break it into 2 parts. The first part is where the kernel is restricted to the points which are sufficiently close to each other. And that is the operator which will have small norm because of all of these things. And the rest will be an operator away from the diagonal where everything is bounded. And so that's how everything works. And I think with that quick sketch, I will stop. Thank you.
Any questions, please?
Is minimal smoothness what you can prove or what you expect to be true?
Well, it's what we can prove. But as I said, there are various counterexamples in the literature which indicate that when properly formulated, this is the minimal thing. It doesn't mean that there aren't other formulations where you can get around this smoothness. Minimal, at least in the sense that something like 2 derivatives are needed. Now, there are different ways that 2 derivatives can be expressed. It could be 2 derivatives which are bounded. It could be 2 derivatives which are positive on one side in some sense. I don't know. There are variants of this, but as far as the 2 derivatives are concerned, the number of derivatives, I think that's minimal. There I can be quite confident that this kind of theorem is minimal. It's just like in the one complex variable theorem. One derivative is minimal, but then there is this tricky condition called Alfor's regula, which turns out to be the necessary and sufficient condition. It's on the boundary of one derivative, but it isn't quite the same, but it's philosophically there. So there must be some kind of version of that.
Other questions? Not, thank you, speaker.
Thank you.